高一刻，手持去喊的李大师你好，苗在打车时事不成，复述服务。可能去喊拿出 CD 机，大哥，苗因为告知对方认错人，收下礼物后让儿子把这 CD 打人。傅大人和李瑶常被认错，图片来源于网络。这段是难忘，我俩真的有点像，互相祝福。他写道。
Hi, let's get started. Good evening all. Thanks for joining in. Today we have Henk Boelman, who is the cloud architect or cloud advocate at Microsoft, joining us all the way from Netherlands. Before we start today's session, I would like to share some of the upcoming meetups that we have. Just going back, we can see we have some of these meetups scheduled even in September until mid of September. And then the most important one or the special meetup we have coming up is the next Saturday, where we have Brendan Burns, who is the co-creator of Kubernetes project. He'll be talking to us about why we should care about microservices. I recommend that you join this session since it's happening on Saturday morning. And then some of the other meetups which our other community members are also organizing. So we have the Microsoft BizApps user group organizing some events on the 26th here. Tomorrow there is the SQL Pass event. There is also Monkey Fest organized by Ben, Xamarin user group. On 25th we have an event scheduled. And then we also have our YouTube channel where all these events from the past, the video recording of these events are available. So please subscribe to this channel. So coming back to today's session, here are some of the housekeeping rules. Please keep yourself on mute when the session is ongoing. You can raise questions by raising your hand, and you can unmute yourself when the Q&A is going on. This session is being recorded, and if you find this useful, please spread the word on social media about our user group activities. So coming back to today's session, as I said, we have Henk Boelman, who is joining us all the way from Netherlands. He is ex-Microsoft MVP in AI, and he's also Umbraco MVP. He is also an instructor at Cloud Guru, and he also is quite active in the community. He runs the Global AI Bootcamp as well as the Global AI Night. So with that, I would like to hand it over to Henk. Over to you, Henk.
Thank you. Hi, everyone, and thank you so much for joining me today. You should all see my screen right now. If that is not the case, please yell.
We can see it.
Perfect. Good, so let's get started. So you already introduced me, but I'm Henk. I'm indeed from the Netherlands, and I'm a cloud advocate at Microsoft. I recently joined, and that is about, okay, it is almost a year, so time goes fast. So this story, what I'm going to tell you today, is about before I joined Microsoft. So before I joined Microsoft, I was a cloud solution architect, and I've built a solution together with the company I've been working for. So I want to show you how we did it and how we used Microsoft AI technology in this. So what are we going to look about today? We're going to first see what the assignment was exactly and what the challenges were. We're going to dive into the solution architecture of the complete solution. We're going to train some basic models with Microsoft Custom Vision, and then we're going to build some more advanced models using Azure Machine Learning Studio. At the end, we will do a recap, lessons learned, do some Q&A, and then it should be around an hour or maybe a little bit more. So first, what was the assignment? So the assignment was that with a phone, with your telephone, you should have been able to take a picture of a package of a light bulb, and that then an AI system can tell you, hey, this is a genuine product, or this is a counterfeited product. So basically what it had to do was look at the box, look at the unique features that make that box unique, and then tell, hey, this is fake, or this is genuine. So, and for that, you need to ask yourself always a sharp question. So lesson 1, when you start with a machine learning project or an AI project, is to formulate a sharp question for yourself. And the question was, is this a genuine or a fake package? Just to make it very explicit. It sounds maybe a little bit obvious, but it helps you train your model. So is it genuine or fake? And these are the type of packages we were looking at. The second thing you need is data, because all machine learning projects need a certain amount of data. So we signed the contract, everything happy, and we were happy, and the client promised us a lot of data, like, because this is a classification project, genuine or fake, we need fake images and we need genuine images. And we asked, like, do you have them? And they were like, yeah, of course, we have them. So, and we were like, after that they signed the project, we were like, can we have the data, please? And they were like, sorry, we don't have any. And we were like, yeah, you're joking. And you're joking. So we were like stuck. We were thinking of creating this all-seeing AI that can look at a box and just, by giving it some sample images, tell us like, hey, this is genuine and this is fake. And that was just not possible anymore. So I want to do a quick poll with you. And you can use the chat window here or on YouTube or wherever you're watching. Tell me which box you think is a genuine box. So which one is not the counterfeit box. So I will look the chat and will hope you put in some answers. Number 3. Number 2. Yeah, exactly, Elias. Yes, they all look the same, and that is exactly the problem. The rightmost one, number 3, number 2. So everyone is quite convinced that it is number 1 is fake. So that is interesting. So I will tell you the answer. Number 2 is the genuine one. And I don't know if anyone knows why, or maybe has seen already the presentation. But I will zoom in a little bit more into the details. So first, let's have a look at the logo. Do you see the difference between box 1 and box 2? If you don't see it, look at the letter L. We see that the font they used is not exactly the same. There it is. And if we look at box 2 and 3, we see that the small icon is different. They didn't have the correct icon set. So, yeah, that is a whole different level of details on the box. And you need a lot of training images to actually make your AI see those small differences. So what we decided is to break this project up in smaller pieces. And also look at those small details where we can actually create a model with less data. So instead of looking at the wall box, we decided to look at, like, hey, for instance, to the logo. Is the logo real? Is that icon real? Should that icon be on this position on the box? So we broke the project up in smaller pieces. So with that in mind, we started creating a solution architecture. And our application is split up in 3 main components. We have an AI engine that does the AI kind of thing. That gets the image, does the prediction, and says, hey, this is genuine or fake. Then there is a management tool where we can manage the AI, see the results, see the analytics, and there is a front end that should run on a mobile phone. And these are the ingredients that we used. So from the big Azure cloud, you can pick your ingredients and compose your application. So we used Azure Durable Functions to orchestrate our AI engine. We used Azure Machine Learning Studio to train advanced models and used cognitive services where they were applicable. We deployed everything, all the AI logic, in containers in Azure Kubernetes Service, controlled the API management, we used Cosmos database, and we used Azure Blob Storage for storing, and we used Umbraco as a management interface. And then we used Azure DevOps and Git and pipelines to deploy the whole solution. So Umbraco config. So we used Umbraco as our backend. And why did we do that? We did that because I didn't want to program a whole kind of backend where I'm going to make endless forms, I have to handle security and all those kind of things, because I wanted really to focus on making the AI engine work. So we used Umbraco, where you can just define document types and easily set up a data store without too much hassle. So in the Umbraco config, you can create one of those products. So you create one of those boxes. You tag it to like, hey, this is this type of box from this brand, from this sub-brand. You upload a front image. Our own AI system runs over that image and checks, hey, there are icons here, there's a logo here, and then we push it to the AI engine. And meaning we push it, I mean we push that configuration to Cosmos database. So meaning that later on we can just put Umbraco away, put something else there, and we can push like the same thing to Cosmos database. And this is how it looks in Umbraco. We have lamps, we have types, we have where the icons are, we have where the logos are, we have like the tag type position. So we know a lot of things about this box. And this is, let's move on to the AI engine. So this is like the boring part where you configure the box. So what happens when an image comes in the AI engine? So it starts all with a photo of the project that is being uploaded to a blob storage. This Azure function, this Azure Durable function, kicks off and starts kicking off all small Azure functions. We do some pre-processing over the image. We're trying to match it to the configuration. We check for text, we check for logo, we check for icons, and then we combine those results. And then we say, hey, yeah, I think this is pretty sure that hey, it is a genuine box. All those Azure functions do nothing themselves. They're just only there for orchestrating. And they call out to very specific business logic that runs in a container, which you can, as an API, so you can test it individually, but you can also build and make it better independently while this whole Azure function stays up and running. And those APIs wrapped in a Docker container can call out to different cognitive services. And the cool thing is that they have their own lifecycle management, application lifecycle management, which gives you the ability to really update that very specific part of the application very fast. So first, let's zoom out a little bit and have a look on what is available on Azure concerning machine learning. So I like this image because it shows you the 5 types of layers. So there are sophisticated pre-trained models, meaning these are models created by Microsoft, maintained by Microsoft, and exposed as an API for you in the cloud. So what you only have to do is you go to the Azure portal, say, click, I want to have a vision endpoint. You get an API key and it is there. Microsoft will worry about the speed, the quality of the model. The only thing you have to do is call an API and get that intelligence into your application. But sometimes you need to build it yourself. And then you need to choose a training framework. And that can be basically everything. PyTorch, TensorFlow, Keras, it doesn't matter, it will run. But doing everything yourself is always quite hard. So we have some productivity services like Azure Databricks, Azure Machine Learning, where we're going to dive in a little bit later, and there are machine learning virtual machines. Machine learning virtual machines are very handy if you start with machine learning and you don't want to be stuck for days configuring your workstation and then finally figure out that you don't have a big enough GPU to actually train these models. So these machine learning VMs are pre-installed with all the frameworks and with all the CUDA drivers, so you can use GPUs when you are training your models. If you need more power, we have CPU clusters, GPU clusters, and we can of course help you deploy it with IoT Edge to edge devices in the cloud, of course, but we can also give you the model and you can run it on premises. So icon detection. That is the first part I want to show you. So you saw the whole big picture. So now we're going to zoom into one of these containers that is going to do the icon detection and validation. So what does it need? How does it work? We get a box as an input. We run an object detection model over it that will tell us, hey, these objects are here. It doesn't tell us anything if they're fake or genuine. If they're like too fake, even the object detection will not recognize them, and then of course we are also done. But it will just tell us, hey, there is a truck icon here, there is a weird shiny thing here, there is a car here. And then we use OpenCV to cut them out. We run a classification model over those icons, meaning that we don't need a very big data set to do the classification. We just need 50 genuine and 50 fake. Then we wrap that up and we give it back to the Azure function. So let's zoom into the lifecycle. So first, if we want to do this icon detection part, we need to have a labeled image set, meaning that we need to have like hundreds of images where these objects are on the box. So for that, you can use the visual object tagging tool. So we didn't have any data. So what we did, we just ordered a bunch of lamps, took hundreds of photos and tagged all the images using the visual object tagging tool. And one of the cool things from this visual object tagging tool is that you can export these images and upload them directly to Custom Vision or export them to a JSON file. Then we used Custom Vision service to train the model, to deploy our model, and we have some Jupyter notebooks that is actually testing our model to see if it's not becoming any worse. Icon verification works somehow the same, only it is a lot easier. We just need two folders, one with genuine icons and one with fake icons. Export them. We did some image augmentation to even create more images. So what we also did is we rotated all the images and we flipped them and so on, changed background colors. So it would really look at that icon and not, for instance, the background. We uploaded them through the Custom Vision Service API. The Custom Vision Service also has an API. I'm going to show you later on a demo how you can do that through the web interface. But you can also do everything from code, which is really cool if you work together as a team. You train the model, deploy the model, and test the model. So let's have a look. We have this icon validator API. That is running Python, it's an Ubuntu, and that is a Docker image. The code in that API calls out to all these different types of custom vision models, which have their own life cycle. So we have the object detection model, the car icon, the truck icon, the shiny thing icon. So this data scientist in our team can really manage the models independently from the code with their own data sets. While our development team can pick that, can just write the software that calls out to APIs. And because it is a Docker container, our operations can just deploy it like it would deploy any other container. So let's have a look at the Custom Vision Service. So the Custom Vision Service is an easy tool that helps you create your own custom image classifiers without doing the data science stuff. So how does it work? There are two different types of projects. So first is a classification project. You upload images of only that thing you want to detect, to classify. Or you can do an object detection project where you actually can have multiple objects in one image, but that means that you have to tag where they all are. So we have sample images, we upload it to the custom vision service, we hit the train button, and we have a model. So classification, one thing, one object, we run it through the model and it will tell us, hey, I'm 90% sure that this is a car. Object detection, on the other hand, works like, hey, I'm 88.5% sure that there is a hologram in this location on this image. Another cool feature from the custom vision service is that you can export these models. You can run them natively on your iPhone, on your Android devices, but you can also get them in a Docker file, which allows you to run exactly the same API in your own infrastructure. Or you can use the built-in API endpoint and you don't have to do anything. So let's have a look at our custom vision service. Let's go for this. Custom vision. It all starts with customvision.ai. You need to have an Azure subscription behind it. But if you have that, you can go to customvision.ai and create a new endpoint. So let's call this Simpsons. I already have a resource created with this button. You can create a new resource and then you choose which type of project you want. So I want to start with a project classification project. We can also do an object detection project, but it takes a long time for them to train, and we want to see some end results in this session. And then we can choose a classification type. So there is single tag per image or there are multiple tags per image. So we are going to do a single tag per image. We're going to use a Simpson data set to show it, because I can't use the real data set from the cars and the trucks here. And then we're going to choose a domain. So here you see general, food, landmarks, retail. So you choose the one that is closest to the problem you want to solve. But here you also see them with the word compact behind. So remember I told you that you can export these models. You can only export them when you train them on a compact domain. Don't worry, you can change these domains also later and retrain your model. So let's choose a general domain and say create project. So we will create a project and now we can start uploading images. So I'll say add images. I will go to datasets, my Simpsons images. You can also download these datasets from my blog. So I will choose 50 images of Bart Simpson and I'll just say, hey, this is Bart. Upload the 50 images. And done there and tagged as Bart. Let's do another class. Let's do Flanders. So we add, we give it the tag Flanders and we upload it. So you see here on these images, I chose a lot of different backgrounds, different angles, but made sure that the light is kind of consistent on the object. And why did I do that? Because otherwise I will create, if I would always create something with this type of background, it will actually think that this black thing is part of the object I want to detect. So you need to have different backgrounds and also different angles and around 50 images. Let's add one more. Let's add Dr. Hibbert. These are 52. We're done. And now the only thing what we need to do is click a train button, click train, and just wait for a few seconds. Like if there are only 150 images in it, this goes very fast. But if you do an object detection project with like thousands of images, it can take like around an hour at least for your model to be trained. But this type of model, like simple classification model with like 2 or 3 classes, can be trained within 30 seconds, but sometimes you have to wait like a little bit in the queue. So let's hope it will actually train, so we can use later on this button, the quick test button, to see if it is actually working. So let's give it like 10 more seconds. I already have trained it, so we can always move to another project. But it would be good to see if this one works. So this might be a good time to, if you have any questions, to throw it in the chat while we wait. Here it is. So we see we've created the perfect Simpsons classification model. There are only 3 tags. The image count is fair. So the recommendation is to use at least 50 images per tag. And also what it recommends is use the same amount of images for every tag. So don't use 10 for Bart and 120 for Hibbert, because then you get a model that will not perform very well. So what we now can do is we go for the quick test. We click browse for an image. So I have some testing images. I should have some testing images here. No, not here, test images. And then we trained it for Hibbert, right? And we see it is 100% sure that this is Hibbert. And these are images that were not in the training set, of course. And this is 100% Bart. So the cool thing what we can do now is we can go to predictions, and here we see which images are coming in through our API. So what we can do is we click on that, and we can add this image by selecting Bart to our data set. So when we train it the next time, it will also use this image for training. So the last thing I want to show you is not here. Okay, that was not what I wanted to do. Image classification. You can go to performance, and then we can actually publish this model. So we will call it test. This resource you've made in you go to test, customization, publish. That will publish an API, and then we can use this in our prediction API. So what we can do now is we can go to Postman. Go to Postman. Paste this URL. Here I have already a testing image from Bart, so I've posted this URL. The only thing what we need now is to copy our prediction key into the headers. It remains the same. So we can now do send. And here we see that it is 100% sure that this is Bart. So this is how you can use it in your applications. If you would have selected a compact model, you're able to export it. So we go back here, and the final thing before I will answer the question in the chat, as I want to see you the object detection. This is not the perfect example. This is just to show you how it works. So the only thing you need to do now is, instead of uploading images, you need to select where these objects are and tag them. So this is a lot more work, and the training takes a lot more time. So if we now go to performance, or we now go for a quick test, we can browse to an image. Let's say we take Ned Flanders, and it should tell us where Ned Flanders is in this image. So it's 99% sure, so that is good. It works pretty well on also Krusty on single images. Yeah, Krusty 99%, but it is having a little bit more difficulties if you put 4 on it. So here the Bart, March, so it's 95, 94% sure that March is there, so that is pretty good. But Bart, Mr. Burns, that's not Mr. Burns, that is Homer, Lisa. Okay, I can see that you would mistake that. So we need to tweak this model a little bit, but this takes a lot of time to do. So does the image type, the SVG, PNG, GIF size, small, medium, large, extra large, have any impact on the classification? No, so what it does is, I don't know the exact dimensions. So it doesn't make any sense to upload like 3 megabyte images, because if you train a model, it always downscales it to a vector, to a tensor. So most of the times you will see it a little bit later in the other Azure Machine Learning Studio. It just resizes it to like 500 by 500 pixels. This is not the measurement, you have to read it actually in the documentation, but let's say it resizes it to 500 by 500. It converts that image to pixels, and then you have R, because it needs numbers as an input. So it resizes it to an array with number, pixel. So RGB coordinates for 500 and for 500 pixels. And that is going into the model. So it will downscale all the images to that vector size. And that also does it with the images that come in to do the prediction around. And I don't know what the input size for custom vision is, but I'm sure it is published in the documentation. So that is custom vision. So if you want to do this yourself, go to AKMS, to this link, and have fun. You can use the Simpsons dataset to do it yourself. So now let's have a look at logo classification. And this is where we can going to create our own model from scratch to classify the Philips logo. We created the Philips logo, but we are going to create it exactly on the same dataset as the Simpsons. So how does this logo classification API works? First, we need to know where the Philips logo is. And because it is quite a readable word, readable font, we can use the computer vision API. Because the computer vision API can detect objects, but it has also a built-in OCR capability. And it doesn't matter if a word is upside down, left, right, rotated, it will read the word for us, and it will give us back the coordinates where that word is. Then we cut out the word Philips. We do some pre-processing with trying to put the word straight, and then we run it to our classification model, and we return the result. So logo classification, it's basically the same life cycle. You label image, you pre-process image, you train your model, you deploy your model, and you test it. And for us, we test it when it is running in a dev test scenario, but of course you can also train the model before you deploy it. So let's have a look at a common way of working if you're working with models. So you have a data scientist that is really good in creating the model, composing the layers, testing if it is working, shaping the data set. But they work in different tools than, for instance, developers. They use Jupyter notebooks, they use a different type of version control, but use Azure Machine Learning to train the model on scale in the cloud. And what it does, Azure Machine Learning can deliver a model and register it in model management. And you can see model management is like a NuGet repository for models. So someone can push it in, say, here is the Simpsons model version 30, it's here. And a developer can pick that model out and write software around it. And that is probably not going to be done in a Jupyter notebook. That is going to be done in Visual Studio or Visual Studio Code or whatever software you need to run this model. Use their own version control, use their own build pipelines with their own checks, and probably wrap it up in an Azure container. So then an operations person can just pull out the Docker container from that container registry and deploy it as they would deploy any other Docker container. So that our Azure function can actually connect to that endpoint and give us back the prediction on the logo. So let's have a look at Azure Machine Learning Studio. So Azure Machine Learning Studio is a service that can help you manage this whole process. So you can work together as a team from data up to running it in production. So it is a fully managed cloud service that enables us to easily deploy, build, and share machine learning projects. So what is it exactly? It is a set of Azure services. So it is not just one thing that is controllable by a Python SDK. Also through the Azure CLI, but the Python SDK is the most robust to do that. And that set of cloud services combined with this Python SDK enables us to prepare our data, to build our models, to train our models, to manage models, to track experiments and deploy models. So let's have a look and zoom a little bit out what a model actually is and what we are training. So you can see a model as a function. And in the old days, I would create that function in a programming language. You have a function, something goes in, something goes out. So we have the algorithm, we have the data, we run it through and I got the answer, true or false. But with machine learning, the computer learns on a different way and it is creating this algorithm for me. So I give it a bunch of answers, I give it a lot of data, I select a training algorithm, and it will deliver me this new function, this new algorithm that it has thought of itself. And in other words, that is called a model. And now when I have that model, I can treat it as a function. So I give it that function data, and it will give me a prediction. And for us, in this example, we're going to find out which Simpson it is on this data set. So you can download it from here and play around with it. So to get started with Azure Machine Learning Studio, you need to do three things. First, we need to prepare our environment. We need to experiment with our model and our data, and then we have to deploy our model into production. Step one, preparing our environment. We have to set up our environment first. We can do that in multiple ways. Please hold on 1 second. I'll be back. Sorry, that was a bunch of friends that came running into my house, as we're all still working from home. Where was I? Setting up our environment. We can do that in three different ways. We can do that through the Azure portal. We can do that in Visual Studio Code by installing AI tools for Visual Studio Code, or we can do it using the Python SDK, for instance, in a Jupyter notebook. And if you've created your environment, you can go to nl.azure.com, and it looks like this. So you see it is a separate experience than from the portal, meaning that it has some more space and you can do a little bit more things. So let's have a look what you get, which things you can do with Azure Machine Learning Service or Machine Learning Studio. It's basically the same thing. So first of all, we have data sets, and that are our register known data set. So I have this Simpson data set, which I'm going to upload and register. So now my data set is versioned. Then there are experiments, and experiments keep track of my training runs. You saw in Custom Vision, I can train and train and train, and that you can see it. You can call that a run, and the whole project is called an experiment. There are pipelines. So later on, when you have everything set up, you can create a pipeline for your training that does the data preparation for you, does the image augmentation, then actually trains it, register your model, and you can publish those pipelines and kick them off later so they can run unintended. There are models, that is the place where you can register your version models, like the NuGet repository I was talking about. So when you're happy with your model, you register it, say this is version 30 of this model, and everyone else with the appropriate permissions can pick it out. Then there are endpoints, so you can deploy your models in Azure, and you can manage those endpoints where your models are running from this tool, and you can manage your pipeline endpoints. So I told you can create those pipelines. There you will find the endpoints and see how much they're triggered, what the deliverables are, their logging, and so on. To do this, we need compute. So under compute, we can manage our different types of compute, and then we have data stores that manage the connections to our data. So let's dive into some code, because I'm going to show you how to do this in Python, because I think if you write it in code, you can version it, and everyone else can see how things became a thing. How did you create the workspace? Which parameters did you use? So here I say workspace, create. I give the name, point of my subscription ID, the research group I want, and in which region I want to have created. And this region is already a very important choice you have to make, because it is bound to the types of compute you can use. So for instance, if you want to use a certain type of virtual machines, like NV6 machines that have GPUs, first check if they are available in the region where you're going to create your workspace. So a safe bet is always West Europe, so I'm creating it there. So you say workspace, create. Takes about 5 minutes and it is creating your workspace. It will pop up that you have to log into Azure, and then it will create it for you. When you have done that, you can say workspace, write a config file. Get a config file, and everyone else can say workspace from config. So you don't need to, so the only thing you need to do is check in that configuration file, and everyone else starts that project with workspace from config. The second thing you need is compute. Here I say Azure Machine Learning, provision a standard NC6 cluster with always one node up and running and a maximum of 6. If you want to save some money, I would put absolutely minimum nodes on 0, because then if there's nothing to do, it will shut down everything and you don't have to pay anything. Third thing you need is a place where your data actually is. We say data store. Get our default data store, because you get one when you create your Azure Machine Learning workspace, or you can register any other blob storage device. It doesn't even have to be in your subscription. So let's have a look at the Jupyter Notebook and start doing this. So what we're going to do is we're going to train a PyTorch. We're going to do transfer learning with PyTorch using Azure Machine Learning. So I always start with importing a lot of dependencies, because that is me. I like them all on top, but tastes are different. And then, because I've already created my workspace, I can say workspace from config. I can connect to my compute target. I've already created it. Provisioning a cluster takes around 15 to 20 minutes, depending on the type of compute. And then I could connect to my default data store. And we will talk a little bit later about experiments, but here I connect to my experiment. So let's do that. You see here, it is using workspace Cybertron. It is using my compute target Optimus Prime, my workspace default blob store, and the Simpsons experiment. We can find it also back here, because here we can go to compute. Here we see that there are 4 different types of compute you can have. You can have your compute instances. These ones run your Jupyter notebooks. There are compute clusters. This one do your help you with your training. So here we have Optimus Prime, and we see one node is up and running. I already spun it up, so we don't have to wait. And then we have our reference clusters, and here this is the place where our deployed models are living. And here you see I've connected it to an Azure Kubernetes service. Click. That is that for now. So let's talk a little bit about data. How does it get there? So we first download our data set from GitHub. You can just download through this URL and you will get your training and validation data set. I unzip the data set and then I upload it to our default data store. When it is there, I can create a data set from that data that is on that data store. So I say dataset, it's a file dataset created from files, and I pointed that it is to the directory Simpsons Lego version 3 and meaning everything that is in there. And then I register it as Lego Simpsons V3. So I can do this, but if I've already done that, I can connect to this dataset by just saying dataset get by name, give me the Lego V3 dataset. So everyone in the team can connect to the same dataset, which is actually quite handy if you're working together on figuring out the best model. So how does it look? So here under datasets, you can see the datasets that I have. Here we have a Lego dataset, and it is loading. So there are 545 files in. It is only 27 megabytes, the first version. This is when I've created it, and here and I edited it. I didn't give it any tags. Can create a new version, unregister, and here it tells me how to use this dataset in Python. Yeah, no, not this one. Good. Go home. Yes. So now we have all the three things we need. We have our workspace, we have compute, and we have our storage. Now it is time for the fun part. It's actually starting to work with our data and trying to create this model that will work. So to do that, we first need an experiment. So I've connected to an already existing experiment because I'm just going to run a new iteration of the model. But when you get started, you need to create this experiment. Just say experiment, experiment, point to the workspace and give it a name. Create a training file, and we will dive in the demo a little bit more how this training file looks like. But this is just a Python file that can also run on your local machine. It doesn't necessarily is bound on a very specific way of running on Azure Machine Learning Studio. So for this demo, I went to the PyTorch website, took a transfer learning sample and just used it. Only a few tweaks that you have to do so it works correctly. So when you have this training file that will pick up the data and transforms the data into a model, you have to wrap that training file into an estimator. And what do I mean with an estimator? So you can see an estimator as a Docker configuration for the where your training script is going to run in. Meaning that you have to specify which environment you want. So I say, give me a PyTorch estimator. I tell it where it can find my training script. I can parse some additional parameters in it. I have to tell it on which compute cluster it has to run, which script it has to execute, if it has to use a GPU or not. And I can specify which conda packages I want. Can we perform transfer learning? Yes, it doesn't matter. It can run any script. You can do transfer learning in PyTorch, in TensorFlow, whatever. It is not bound to a specific thing you can do, as long as you can run a script that delivers you the model. So you can install conda packages, and then you specify which type of framework you want. And then when you have your estimated configuration, you have to submit it to your cluster. And when you have submitted it, you can ask for the details. You say run details, show me the details, show me what is going on. So let's do that and train ourselves a model. So let's first preview the dataset. Let's see what is in the dataset. So there are 10 Simpsons in, exactly the same as what we used for custom vision. So and this is the training script. So I went to the PyTorch website, went to the tutorial for beginners, and looked up a transfer learning tutorial. Went to GitHub and copied this script. And I removed the last bit because I didn't want to visualize my model yet. I just wanted to actually train my model and have the outputs from that. So what did I do? Oh, absolutely not that. What did I do? I copied the script and I added a reference so that I could parse incoming argument and that it can connect to the actual context where this training script is running in. And then I have this run variable where I say run get context. I parse my incoming arguments. In this case, I want to know where my data is and how many training rounds I have to run it through. Parse the arguments, and then I'll prepare the data set exactly as they show in the example. And here you see I resize everything to a 224 by 224 image. I have my image data set here, the class names. I check if I have a GPU available, and then I start training the model. So I create a for loop for the number amount of epochs are there, and then I do in every phase, training and validation phase. And here I've added this line. So I say run.log, in this case, the phase it is in, like training or validation, and then the accuracy and the loss. And I'm logging a float. So because it is every training, every iteration, the same name, it is starting to draw a graph for me. I will show you a little bit later. So I'm training this, and then I save the model. So this is important to know. You have to save everything you want to have saved in the outputs folder. So you save the model in the outputs folder. And then what happens is it automatically copies this outputs folder back to your experiment. Because this Docker container will shut down when it is done. When your training script is done, when it is here, it sees, oh, nothing is going on anymore. Let me shut down, and throws away the container, and everything you have done is lost. But if you save it in the outputs folder, it is copied back to your experiment, and you can access it later. So let's write out this training script and create an estimator where it is going to run in. So I tell it where it can find my data set. So I say Simpsons dataset as a named input Simpsons dataset and mount it. So now it is available as a virtual directory in that Docker container. So for this script here, it is just looking in a directory while it is my version dataset. I say used 15 training rounds. You can find all the scripts in the directory training scripts. The only thing for me here is now train.py, but if you have like a big project, you will probably have some more libraries. I tell it on which compute target it has to run, which entry script it has to use some GPUs. Here I'm using the pip package manager to install some extra things, and I'm telling it to use the framework 1.3. I'll run this cell, then I'll submit this estimator, and then we can ask the details from this estimator. So my cluster is already running, and I've run this experiment already a few times. So it doesn't need to create this Docker container for me. It has already done that. But the first time you do this, it is creating this Docker container, and that takes a bit of time. But the cool thing is that it registers it for you in your own Azure Container Registry that it has created while you are creating your workspace. So you can connect to that, pick out this Docker container, and see exactly what is going on in there. So here we see that it is running. This is how fast it can go. And then hopefully soon we will see that it is mounting our Simpsons dataset to the directory /temp. And then soon it will start downloading our base model and then start adding our new data. So here it is running, it is downloaded. It is now busy with the first training round. So in here by the first we see it is logging the training and accuracy here. But we will see that when it is doing the second round, it detected, hey, these are multiple floats coming in the same variable. Let's create a graph from it. So here now we can see the accuracy improve. Hopefully, if your model is good and the training and your loss is going to go. So let's get back to the presentation where I can actually explain you a little bit more what is going on under the hood. So we have this Azure notebook or Jupyter notebook. I submitted this estimated to my experiment. What it did then, it snapshotted the whole folder, everything what is in there, and copied it over to the experiment. So my training script is also now versioned in the experiment. So everyone can go to the experiment and read back what is happening. It's created a Docker image according to my estimated specification. It deployed the Docker container to the compute target and mounted the data, my data set. That is, of course, on a data store. It launched the training script and it started streaming the output to the experiment. And because I had the widget installed on my Jupyter notebook, it also made the information available there. And then when it is done, it copied over the output also to the experiment. So now the model or the outputs are at the experiment in that specific run. So the next thing we have to do is to register that model and model management. So we say run, register a model, give it name it Simpsons.ai, and you can find it in our outputs folder. So that is that. So that is there. And here we see that it is actually done. So we can ask here what the status is, saying run.status, and it says completed. We can also connect to previous runs by just using the ID. So what we can do now is we can register the model. We say run.register model, we give it a name, and we can specify some more information. So for everyone, it is very clear what this model actually is. So we say which framework we use, which framework version, we can give it a description, we can give it actually some tags for which conference this one was created, and we can specify which resource configuration it has to use. So we say CPU is 1, memory is 2, and we can here say register. So let's register it. And we see version 31 is registered. So what I now want to show you is if we go to our experiment, Simpsons PyTorch, it's obviously the last one. So this is my time here. It took like 2 minutes. You can click on that run. And here we can see now which compute target was used, which data set was being used, which Git repository backed it. We can find our outputs here. So here we can actually find our model and our labels. We can see the snapshot. This is the training script that it is used. It was the only thing in our project directory. And here we have some new preview features, which I highly recommend that you take a look at to see if your model is fair and how you can explain it. So from there, we can now go up and down. So I know we're almost 2 minutes before time, but I'm going to take 5 more minutes and show you how we can deploy this model to somewhere. So if you want to do this, go to this website. Yeah, there's a whole tutorial about how to train this type of model. So step 3, deploy your model into production. For that, we need to have, of course, the model. We need a script that actually runs the model. And we need an environment file that will specify how the environment has to look, where we can run our scoring script and our model. It will wrap it up and build a Docker image for us, which we can deploy to an Azure Container Registry or a Azure Kubernetes service. So this is how a score.py file will look like. You have an init function that will actually load in the model, because loading in models take time. And then there is a run function that does predictions against the model. There's an environment file that will specify through the Conda package manager which packages need to be installed. And then you combine that in an inference config. And that inference config you can use to deploy it to an Azure Container Instance or to an Azure Kubernetes service. Deploying to an ACA you can do from code. You say Azure deploy configuration, 1 core, 2 gigabytes of memory. So you say model deploy using this inference config, this deployment config, this model to that Azure Container Instance. It is basically, it's really 2 lines of code to do that. Deploying to AKS is 1 more because you need to connect to your AKS environment. So let's do that, and then we have it up and running. So you can download your model here. Let's do that first and see if our model is any good. So I'm downloading this model, the outputs, and here I have a script that will actually run our model. So we know before we deploy that our model actually does something. So here we have BART, NET, Mailhouse. It is looking okay. For 2 minutes of training, it's looking very well. So now we're deploying it. We need that scoring script. Init method that loads our model in. And here is the run method that does the exactly same pre-processing over the image that we did for the training. So we resize it and we crop it to 24. We create a tensor from that and run that tensor through the model, and we return the result. So we do that. We specify our environment. We need PyTorch and Pillow and all those things installed. We create an inference config, and then we can deploy it to this Azure container instance. So I'm not going to do that. It takes like 5 minutes, but I've already done that. So we can ask for the scoring endpoint. So you can click on that, and then it tells us, hey, I need a URL as parameter. There is a simple way of testing this. So we can use Azure Container Service, Azure Container Instance Service run, and we can post JSON to that. So here I have a file with a lot of URLs. So it will post those URLs for me in a loop, and we should be able to see the same result. Can be deployed to other cloud providers for Kubernetes deployment. It's basically just a container you're creating. You don't have to use this type of container and this deployment mechanism. You can create this container, pick it up from your container registry, and deploy it wherever you want. But if you use this, here we see the results. So our API is working. But if you use a connected Azure and connected Kubernetes service or this ACI, you can find things back in endpoints. So this is where we just deployed it to, or I did it just before this presentation. And here we can see which model it is. We have this model, we see which runner it is generated, and we can track it back all the way to the dataset. So that is the power of Azure Machine Learning Studio. From data up to where your model is running, we can make it traceable. But it doesn't mean we cannot deploy it in our own infrastructure, because probably you also don't want to deploy this using a few lines of Python. So I always say there must be a better way to do this. And yes, there is, but that takes a whole other presentation to show you how to do that. But we can use Azure Machine Learning Service pipelines in combination with Azure pipelines to build and deploy these models so it fits in a whole continuous integration scenario. A small recap, because we were detecting counterfeit products. So we used an Azure function, an Azure durable function, to orchestrate the whole and all these models that did a very small part of the job. We used custom vision for the easy models. We used Azure Machine Learning Service to create the more advanced models. We made everything available as Docker containers and gave them one specific task to do. And we deployed everything. We used Git, CI/CD for every component from the start. So our lessons learned, of course, you always have some lessons learned after a project. You never have enough data. It is always a problem with machine learning. So we created our own data, and we were lucky that we were able to do that, but you're not always able to do that. So before you start a project, make sure of your data. It always makes things easier if you apply DevOps practices from the start. And sometimes, like what we did, we were trying to create this almighty seeing AI thing. But that is not always the way to go. So you can break your problem into smaller pieces to make it easier for you. So think big, start small, and you can grow very fast. These are the resources. The slides will be available. I'll post a link in the chat. And that's it for me. So we can answer some questions. I still have some time for that.
We have a couple of questions, Hank. One is regarding the support for C# language, and the other one is regarding the transfer learning.
Yeah, so I don't know. I don't think it has support for C# language yet. On the other hand, it are all API calls, so can be. I don't know if there is an SDK for C#. I don't think so. Can we perform transfer learning? Yeah, it is basically what I showed you is a transfer learning script, but it is language independent. So you can train whatever you want, as long as it is in Python or R, if I'm correct. How do you make these awesome slides? You spend a lot of time on them. But thank you.
So now that the session and the demo is done, if anybody has a question, you can unmute yourself and ask the question. I had a question, Hank, about the quality of the images and the, like you said, the data is quite important. Are there any industry standard images available, like for logos and things like that? I read somewhere that there is the capability within Azure Machine Learning to identify logos. So do we have a set of standard images, the logos of well-known companies available?
And now how that works is what I did. Let me go back to my browser. I think you're talking about, it was here.
Yeah, domains. Yeah, I was talking about.
Yeah, but you still have to upload samples from your image, and then it will downscale it to the vector it needs, because that for every image it has to be the same, and then it will run that and use that in your training algorithm, because it is just looking at numbers. Eventually, a big array or multi-array with numbers. So the easiest way is always to use that the MNES dataset, where you have the small the letters with black and white, because black and white classification is easier. So what it basically does is it looks at the 16 by 16 pixel image. It finds the gray value, so the RGB or the B value, the black and white value in this case, between 0 and 255. And it creates a big string or a big array of all those numbers, and that is what it learns with.
Okay. Thanks for the feedback.
And the other thing is, it is just the bigger your images, the longer it takes to train. So it is always the doubt your data scientist makes what type of images it's going to use if you train it yourself.
Okay. Anybody has any other question? Okay, I think if no other questions, then we can close the session here. Thanks, Hank. Thanks a lot for taking time during your afternoon hours. It's been a great session. I learned a lot personally from this, so thank you.
Yeah, and everyone feel free to send me a tweet if you need help with this.
Thanks, guys. Thanks a lot for joining. Bye-bye.